en varios sentidos. Está fuera de programa, pero además tenemos la extraordinaria visita del doctor Bill McDonough de la Universidad de Maryland y también del Department of Earth Science de la Universidad de Tohoku. Para quienes no lo conozcan, Bill es una persona que ha dedicado toda su carrera a entender la composición de la Tierra, por qué la Tierra tiene la composición química que tiene, y eso básicamente involucra el estudiar desde cómo se formó la Tierra. Eso le ha permitido tener uno de los, ser de los autores de ciencias de la Tierra más citados, y como ejemplo de qué tan citado es, al menos en mi trabajo, pero creo que en el trabajo de mucha gente que se dedica a la geoquímica, es que ahorita, poco antes de venir para acá, estaba buscando en mi programa de correo electrónico un mensaje que me había mandado Bill hace varios meses de su currículum, y yo simplemente puse en la barra de buscar McDonough, y me salieron como 20, 30 correos de tesis que no tienen nada que ver con él, bueno, que no tiene estrictamente de tesis, de trabajos, de artículos, que básicamente la máquina de buscar es tan eficiente que encuentra en las referencias el trabajo de Bill McDonough. El trabajo de Bill McDonough lo tenemos todos de una u otra manera metido en nuestros trabajos, cuando estamos normalizando un diagrama de tierras raras, cuando estamos viendo cómo viendo la composición condrítica de la Tierra, y es alguien que se ha dedicado esencialmente a entender cómo está compuesta la Tierra y más recientemente otros planetas. Nada más, él define su investigación como comprender la composición, estructura y evolución de la Tierra y otros cuerpos planetarios. Ajá. Eso es básicamente la línea dominante de su investigación, pero también trabaja mucho en el desarrollo de métodos analíticos de vanguardia para diferentes aplicaciones forenses, arqueológicas y más recientemente también espaciales. Sin más introducción, quisiera dejar el micrófono a Bill. Les voy a pedir que las preguntas las dejemos hasta el final. Tenemos suerte de que estamos podemos conectar esta plática a diversas partes de México. Tenemos gente conectada desde el CICESE, Ciudad del Carmen, incluso gente de Guatemala conectados. Entonces, si también tienen preguntas allá, por favor háganos saber.
Muchas gracias, Juan Pablo. Sorry, I do not speak Spanish, but I am very, very grateful to be here, to have the opportunity to meet and talk with many of you. I had a fantastic time yesterday learning about the geology of the region. So it is my pleasure to be able to share with you some of the thoughts and ideas that I've had over the years. Now, in talking about determining the composition of the Earth and Mars, I want to highlight that Takashi Yoshizaki is my PhD student at Tohoku University in Sendai, Japan, where I'm also a professor. And so we have just recently submitted 2 papers, Takashi and McDonough. So he is the lead author on both of these papers. And I'd like to acknowledge the great work that he has done. He was interested in the work that I initially did as part of my PhD on the composition of the Earth. And we have meetings that last from 1 to 4 hours once a week when I'm in Sendai. And he kept asking me about questions of how did I determine the composition of the Earth? And so this is the story I will build for you today. And he says, can we do the same thing for Mars? And so he had the great desire to sort of say, let's go somewhere else and do this. And it's been a very fun journey. So for, I guess, a few decades now, I have given what I would call a prescription for trying to describe a model by which we use to build the composition of the Earth, the terrestrial planets, and for that purpose, we can also use it for exoplanets. I have been, let me call it, dabbling in the field of looking at exoplanets and predicting their composition. So I start out with astrodetic, geodetic seismic constraints. Geo would be, of course, the Earth, but it's commonly referred to it as geodetic data for Mars and the Moon. Geodetic data would describe the shape of the body, the spin, etc. The seismic constraint is perhaps the most powerful of all our information for both the Earth and the planets. So from a geodetic measurement, we'll get the mass of a planet, we will get the mean density of that planet, we will get its shape, and from its shape we can calculate what's called the moment of inertia, which tells us about the radial density distribution. So any geochemist that's going to come along and try to identify the planet, it must satisfy those constraints. It's been exciting this year working on Mars because we know that we will have a ground truth moment when the satellite that's sitting on Mars, the Mars InSight mission, finally gets a seismic signal from the planet interior. I do know of work on this InSight mission, and they presently have several magnitude 2, magnitude 3 earthquakes, insufficient for identifying the equivalent of the 410 seismic discontinuity in the Earth, insufficient defining the core mantle boundary. So I was excited to, let's say, use and build this model because we will have a ground truth event. We will, once we have a big enough earthquake on Mars, and it will happen, we will be able to evaluate how right or wrong our model prediction is. I will finish this talk highlighting a new field of earth sciences called geoneutrino research, or neutrino measurements. And I'll talk a bit more about that topic on Friday. And from that, we can also ground truth a model that was put forth by myself some, I don't know, more than 10 years ago. I'd like not to count that up. So that's the rest of the story. The rest of the story is really based upon the kind of work that I do on a daily basis, which is measurements of chemistry of the Earth. So that would be the chondrites, the composition of the solar photosphere, chondritic ratios, and non-refractory ratios. That's the realm of the chemist in me. Now, we have things called chondrites. These are the most primitive meteorites, and they're actually a mixture of metal and rock. And that mixture of metal and rock is primitive, and it tells us really about what might be the mixture of a core and a mantle for a planet. And these are very key. We often refer to the chondrites as the building blocks for planets, and I will use that term a few times. The composition of the photosphere of the sun, that's the skin surface of the sun. If we look at the ocean, we see it's blue, but we cannot stand on it. If we look at the sun, we see it's white, and we cannot stand on it, even if we could withstand those temperatures. But we can use absorption spectrometry to measure the relative abundances of all the atoms seen in the sun. And I will talk about that because for 50 years we've used this information. Chondritic ratios are the refractory lithophile elements. Lithophile means these elements do not go into the metallic part of the planet. They stay outside of that. They'd be in the crust and the mantle. Chondritic ratios would mean the chondrites in planets have these same ratios. It would be the same as saying the calcium-aluminum ratio. So you'll see calcium-aluminum. It would be the same as saying the thorium to uranium ratio because we can measure that quite precisely. Then finally, the non-refractory elements, magnesium, silicon, iron, and oxygen, for example. These are the big four. And then elements like potassium and rubidium, these are the volatiles. So all of this needs to be put together to describe the Earth. Let us take a quick setting of where we're at. These are the planets in our solar system, and when we were in elementary school, we learned that the inner planets are rocks and the outer planets are gas giants. And so it is worth asking that question, why? It is wonderful to have a 2-year-old spirit inside your body or a 2-year-old next to you who will ask you why. Now, it could be that if I get this story right, I can give you more reasons as to the why there is already differentiation in our solar system. So differentiation means there's no gas in no gas volatiles in the terrestrial planets, and there's plenty in Jupiter, Saturn, Uranus, and Neptune. So that differentiation, chemical differentiation occurred, but we have ideas as to why. The other part of this figure in the lower portion shows you the rocky planets, and the takeaway from that is some have very large metallic cores and some have very small metallic cores. Again, I ask, why? A very important question to always ask. And so from this, the situation for looking at the Earth is relatively easy. We have seismic signals penetrating through the Earth, and it defines for us exactly how deep the core is. We have geodetic measurements that tell us how tall and fat our planet is. We have geodetic measurements that tell us what is the mean density. So when we fit a chemical model, it must fit that parameter space. But for the Mars, we don't know the core mantle boundary, so we can fit a finite number of models, but the number finite is quite large. So that's another point of, let me say, uncertainty. So we'll begin with the details. On the X and Y axis, we have two different reference frames. On the Y axis, we have the abundance of the elements in the solar system as measured in the spectra of the sun. And on the X-axis, we have a measurement we can do in our laboratory, which is the abundance of elements in a chondrite. Specifically, the one used here is called a C1 chondrite, which in the cosmochemical community has been elevated to the position of the most primitive. We actually don't know that for certain, but it's a very, very good reference frame, because if you are paying attention to this section, where the elements magnesium, silicon, and iron are cited, this scale is actually 1 million atoms of silicon from the chondrite and 1 million atoms of silicon from the sun. We don't know the actual number of atoms of silicon in the sun, we just normalize it to 1 million. But from that point downwards, magnesium, silicon, iron, through the rest of them, over 6 orders of magnitude, the concentration matches 1 to 1. Now, I think the important takeaway is in the top left where it says the sun has more than 99% the mass of the solar system. To put it in perspective, when you start to feel very proud, Jupiter has 1 part in 1,000 the mass contribution to the solar system, and the Earth 1 part in 1,000,000. So in this solar system, us and this planet represents only 1 part per million. What we can see right away is that the sun represents a good metric for what might be the composition. But we already know that planets are different. That is, the gas giants don't look like the sun. Here is the problem. Prior to my PhD, throughout my PhD, for many decades after my PhD, I said the sun was the best metric. And we were using it from what we would call the abundances in the photosphere. So that would be photospheric spectroscopy. But what we can see now is that the compositional model from photospheric spectroscopy and from something called helioseismology, we're looking at acoustic waves passing through the sun. We get 2 different answers. We can say we know how much hydrogen, we know how much helium, and then for an astronomer, all the rest of the elements are just considered one element, and we call that Z, mean atomic number, if you will. And the answer from the photospheric spectroscopy does not match helioseismology. And that's been a problem for more than a decade. Now, recently, in the last few years, we have particles that have been spewed out of the North Pole of the sun. We have collected and analyzed these particles, and that doesn't match the solar photosphere spectrum. And most recently, neutrino physicists have measured the neutrino contribution coming from the sun. And it's finding a different composition for its mean atomic number. These neutrino emissions are different from where they're sampling the helioseismic signal and the solar wind signal. But these three measures all agree. So that is the most interesting statement. And it raises question into what is the solar photospheric measurement telling us, or what is our estimate from the local thermodynamic equilibrium? Might there be a problem? Now let us identify what are the elements to focus in on. So the light blue at the bottom, and what you'll see is the Y scale. The Y scale goes to 0.88. Virtually all of the chondrites, all of the potential building blocks, and we actually group them into simple flavors of carbonaceous, ordinary, or enstatite. The details are not important, they're just different types. They all have 90% of their mass made up of the element oxygen, iron, magnesium, and silicon, 4 elements. That's really powerful. You can describe the terrestrial planets by 4 elements alone. If we add to it, in the red, 3 more elements, calcium, aluminum, and nickel, I've pretty much described 98% the mass of a planet. And for the Earth, you can see that I'm pretty close to 99% by just these 7 elements. And if I throw sulfur into the mix, we're over 99%. So 8 elements can describe the Earth. Now let us put in perspective meteorites. There are generally 2 types of meteorites. One that we saw falling down from the sky. One of the most famous ones is the Allende meteorite that fell in 1969 in western Mexico. And those that are found by farmers and other people who walk around them. And they call those finds. They found it by accident. The falls are the ones that are important because if we actually look at it, you can see this is meteorite fall statistics. 1,100 meteorites were observed falling from the sky in approximately 1,100 years. So the number of finds are approximately 1 a year. But at the bottom left, you'll see right away, there's a bias. That means we have samples that have come to Earth only recently. So it says here, most studied meteorites fell to the Earth less than 100,000 years ago, or 1/10 of a million years. And you can see that 80% of them are the ordinary chondrites, and only 4 and 2% are carbonaceous and enstatite chondrites. We make a lot of stories about this information, but I would highlight that the primitive undifferentiated meteorites, ordinary, enstatite, and carbonaceous, are very different proportions. Here's another interesting thing. Again, remind ourselves, less than 1 million years of sampling of the asteroid belt. Well, the asteroid belt is highly processed. This is a frequency on the y-axis, radial distance out from the sun on the x-axis. And what we're looking at are just the population of meteorites in the asteroid belt. And a long time ago, more than 1.5 centuries ago, it was identified these Kirkwood gaps. Now, the Kirkwood gaps mean there's very few asteroids in that zone. And as it's highlighting on the screen there, you can see ratios like 3:1 and 2:1 and 2:3. And that means for every 3 times the orbit of that portion of the asteroid belt, Jupiter has orbited once. And so this is actually what we would call gravitational resonance, and that Jupiter and the sun have essentially worked together to gravitationally clear out these regions of the asteroid belt. Already, we have to worry about the bias in the delivery of samples of the chondrites to our solar system. Well, I should say to the Earth, sorry. Stepping back once again, I have talked in terms of proportion of elements, but I have to remind myself that people look at this question differently. So 2 slides ago, I represented the story actually in weight % space. But if we look at it, 1 out of 2 elements on this planet is oxygen. The top figure is the atom proportions. And you can see that even though you can see that there's something like 30+% iron in the Earth, that's by weight %. It's only about 15% by atomic proportion. So here we can look at the elements, and we can again ask us, if we have 9 elements to describe the Earth, what would the order be? And we'd again see it's most abundant are iron and oxygen, then magnesium and silica. That sets 2 things. That sets the size of the core in combination with how oxidized the planet. If the planet is completely reduced, the core might be enormous. If the planet is completely oxidized, there might not be a metallic core. The portion of my talk that I will finish with is considering habitability of the planets. And a fundamentally important aspect of habitability is whether or not we have a magnetic shield or a magnetosphere surrounding the Earth, attenuating the cosmic ray flux. Therefore, the proportion of oxygen to iron is fairly important in helping us to decide a planetary habitability scale. And so I think that's an important point for us to consider. And for petrologists, they tend to think of this as the redox state, the oxidation reduction state. And for us, we think about our planet as being blue, and we think about Mars being red. The surface oxidation does not tell us about the interior oxidation. Let me just give a few more items of information about the Earth, and then we'll have a fun time trying to figure out the composition of Mars. I find this figure to be informative to myself all the time. I look at this and I've stared at it. It's a figure I've created. But it reminds me, the first thing I'll tell you is over on the far right, you have a fair amount of information on the temperature with some uncertainties. And some of these uncertainties are what we would call statistical, not systematic. They do not tell you the assumptions involved in this characterization. The center of the Earth we can consider to be about 6,000 Kelvin, which is approximately the temperature of the surface of the sun. At 6,000 Kelvin, how do we get that? Well, simply stated, we get our best mineral physicists to look at what is the pressure of the inner core, outer core boundary, and that would be about 336 gigapascals. And in simple phase petrology space, at what temperature does iron crystallize at 336 gigapascals? It's really no more sophisticated than that. The weaknesses are there's light element in the Earth's outer core, and there's probably half as much light element in the inner core. But the best we can do, because it's technologically challenging, is to measure what is the crystallization temperature of iron from a liquid at 336 gigapascals, and that's our constraint for the core mantle boundary, the inner core, outer core boundary temperature. The next two, 4100 and 2730, really tell us the temperature on the core side of the core mantle boundary and on the mantle side of the core mantle boundary. This is a very big unknown. It's about 400 degrees on the core side because we just don't know what that temperature is. On the mantle side, it's really not the temperature exactly at the core mantle boundary. That's a conductive layer because there's no mass transport, there's no advection across that boundary. So we're conducting heat across that boundary. And that 2700 temperature really represents the base of the adiabat. So maybe 200 kilometers off the bottom of it. And that's not known so well. It's extrapolated from what we would call the transition zone. The base of the transition zone is where we have phase changes. That is ringwoodite breaking down to bridgemanite plus ferropericlase. The importance is that we go from one phase to another at that pressure. And we can study the temperature at which that phase reaction happens because we know the pressure. It's actually measured seismically at 660 kilometers. The other one is at 410 kilometers, even more precisely measured seismically, even more precisely measured petrologically. This is the one point inside the Earth's interior we know the temperature really well. Everywhere else is much more prone to assumptions. And that temperature, I think, is, I can't see it so well. 1830. I can't remember these numbers. Then we have the temperature about the middle of the upper mantle and the surface potential temperature. We will use the surface potential temperature. That's the extrapolation of the adiabat to the surface. We'll use that on Mars because I'm going to make some assumptions on Mars. And here, this red thing called the mantle geotherm, it has two slopes. The steep slope at the top is the conductive gradient. The less steep slope is the adiabatic gradient. And what you see over here is a little jig-jag. It goes high, and then it goes, and that's because there's an endothermic reaction reducing the temperature beneath that by just about 10 or 20 degrees. And this diagram here would show you, I have my assumptions, isochemical. The top and bottom of the transition zone have the same composition. I use a particular model called pyrrolite, and that's compositional. I assert that the magnesium number, the proportions of magnesium to iron, is this number 89. And the geotherm, that is the rate of change of temperature with depth, is published in a paper. And from that, I get those temperatures. That's how I got those temperatures, really. And these mode proportions of different minerals, you can see the left half is just olivine going through a series of phase changes. And we'll see a difference here between the Earth and, and Mars. And we'll see a difference in the thickness of the transition zone. Finally, for the Earth, what we have here is a model composition that I published in '95. And the y-axis is normalized to a chondrite reference frame and aluminum. So the amount of aluminum in the Earth and the amount of aluminum in the chondrite is the same. That's why the horizontal line is 1. And then what you can see at about 1350 degrees Kelvin, using the top x-axis scale, is you'll see europium, magnesium, and silicon. And that's just basically saying I did not assume magnesium and silicon to be the same as aluminum. That's where we begin to deviate from the chondrites. So what I spent a fair amount of time on is really these elements here. And these are mostly the left column of the periodic table, the alkali metals: lithium, sodium, potassium, rubidium, cesium. If I can get that right in terms of estimates, I would essentially end up knowing what is called the Earth's volatility scale. I've worked a lot with petrologists, but when I do that, I say, I don't know how it got there. So if you're going to conjure up a model for how, this is how the Earth was made, it must follow this recipe: so much potassium, so much lithium, so much rubidium. If you want to do something different, you have to explain why your Earth does differ with mine, and then you can then say how it happened. So I emphasize the first fact is I think I can do the geochemistry, and all of us can do how it happened. So there's a separation in the science information. You'll see a few other elements like boron, zinc, and fluorine is off the scale, but it could be included. So this is really the time integrated signal at one astronomical unit out from the sun. So it could have had a lot of volatiles in the beginning or a lot of volatiles later. And that's really referring to the accretion of volatiles and when. I don't know. Here's some of the more exciting science that's happening right now. There are a number of scientists who in this room might be good at mineralogy, may not be good at astronomy, but there are a number of experts now in what's called astromineralogy. And they measure the mineral spectra in planetary disks that are accreting present day, also in the interstellar medium. They measure how much olivine or pyroxene or quartz or iron sulfide called troilite. They also look at the radiation damage in those minerals in the interstellar medium and in disks like this, and they compare that there's annealing in the disks. And you can see here two simple minerals, olivine and pyroxene. And they're really simple because olivine has 2 magnesium atoms for 1 silicon atom, and pyroxene has 1 silicon atom for 1 magnesium atom. Very simple. And to date now, there are measurements on these disks that says there's a lot of olivine close in and a lot more pyroxene further out. And then other disks have a lot more pyroxene close in and a lot more olivine further out. So the system's dynamic, and we have to understand why. We do not know why, but we would assume that there is a temperature dependency. Planets do not have to be chondritic, and all I'm doing is emphasizing here that people have assumed magnesium-silica ratio is chondritic. I will have a diagram on that. Next exciting thing. So I think it's very exciting that astronomers are now doing astromineralogy, helping us. Next exciting thing. Cosmochemist. On the left diagram, we have a very strange unit in the y-axis, epsilon 50 titanium, on the x-axis, epsilon 54 chromium. But these are isotopic anomalies in titanium and chromium these are nucleosynthetic anomalies. Some of them can be mass-dependent anomalies. But what it shows you is there's a red field and a blue field. And in between, I and some others have called this the Warren gap. And what we really mean by the word Warren gap is the blue dots are not ever seen in the red field. The red dots are not seen in the blue field. And so because of that, we have interpreted that as limited radial distribution of components in the accreting solar disk, protoplanetary disk. This observation, Paul Warren first came out with it in 2011. And for the last 5 years, a cascade of papers come out reinforcing this. This is now documented in something like a dozen isotope systems. And we can actually extend it further into elemental ratio systems as shown on the right screen. And we find that the Earth and Mars more associated with the red flavor as opposed to the blue flavor. And the blue flavor is interpreted to having its spatial origin out by Jupiter. So when the Martian model, there is a perfectly fine Martian model composition out there. It was created by Heinrich Wanke and Gerlinda Dreibus in around the 1970s, 1980s. And they said the chondrites equal the solar photosphere, the solar system, and therefore Mars. And that was their assumption. And today I would say I don't need that assumption to make my conclusions. And of course, it goes back to that original XY diagram where the chondrites look like the solar photosphere. And they say the chondritic abundance is the absolute abundance of aluminum is equal to that in C1 chondrite. The difference between 1978, when they first started coming out with this, 1980, 1985, 2000, the difference between then and now, I have lived through this. 1980 was a very controversial year. Several scientists, about let's call it a handful of scientists, went to the Lunar Planetary Science Conference and argued these meteorites are from Mars. And believe me, nobody believed them. And it turns out now, these meteorites are from Mars. And we actually have an abundant chemical and isotopic evidence to support that conclusion. Evidence that we've measured on the planet. So we know what the atmosphere is. We know what the isotopic abundance is out there. So what we can see in the top row is sugartite, knocklite, and not chasignite, but another meteorite that was once decided to have life forms fossilized into it. But we do not find any evidence for fossil life on Mars yet. Then on the bottom row, we say Mars Odyssey, Mars Express, and a family of satellites and rovers now track all over Mars and tell us a lot about the planet. And they reveal for us the interiors. How did we do it? Oh, one other point. We have a global compositional map too, because it has a very thin atmosphere. Gamma rays can be emitted from the surface of the planet and be detected in space in orbital satellites. And what I'm showing here is on the left side is the thorium signature for the surface of Mars. And you can see there are red and yellow areas and blue areas, areas that are thorium rich and areas that are thorium poor. It's no different from the Earth. We would find such rare, significant differences on the Earth. But from this, we can get a gamma emission from thorium. We can get it from potassium. We can also get it because of the bombardment from other elements like silicon. So we use global observational data, and we use data from the Martian meteorites. And we can start out with certain assumptions, as I'm showing here. Major element compositions, relative and absolute abundances of the refractory lithophile elements. That is, the elements that we can actually measure, those elements that didn't go into the core. And then, of course, the other component is we have to get the moderately volatile component. So I will start, this will be 1, 2, 3. I will go through how we were able to determine each one of these for Mars. It's a complicated diagram, but I wanted to show you 4 different versions of it, just to show you that we can do it again and again and again for about 20 elements that are refractory lithophile. And we take the data from Martian meteorites, and they give us this array. So you see an array of pink and red data. Not the best correlation. That doesn't matter. What you can see on the X and Y axis is 2 elements. In the top left, it will be terbium, scandium. On the X-axis, it will be gadolinium, calcium. And if you look at these 4 diagrams, I'm using different ratios on each of them. And from that, we have a cross that's in gray. And it's at the 1, 1 point, because all of this is, you'll see a subscript, CI. It's all been normalized to the chondritic ratio. And what we can do is for about 20 different ratios, we can do more, but for about 20 different ratios of refractory, AB ratio versus a CD ratio, we can see there's an intercept with the chondritic ratio, the gray to gray bar. And from that, so it's that point there, they're all going through that point to a lesser or greater extent. We have demonstrated that the planet has chondritic ratios of refractory lithophile elements. Okay, that was a big step. The next step is, well, what's the absolute concentration? In this case, europium, terbium, lutetium, gadolinium. And that's what we did. When the correlation array crosses the chondritic ratio, in the top left space, it's titanium, scandium. We get a value that is shown as an arrow with the label BSM, bulk silicate Mars. And that would say that relative to chondrites, europium is around 2.3 times the chondritic normalized value. And you can see that terbium is about 2.5, gadolinium about 2.2, lutetium about 2.6 or 7. And that ended up giving us 2.4 plus or minus 0.3 uncertainty for the entire ensemble of ratios. That was a very important starting point. It was the same starting point I had for the Earth. Once I knew the calcium content, the aluminum content, or the thorium content, or the uranium content, or a rare earth content, I could just multiply it times the chondritic ratio and get the other element. So in fact, I knew 36 elements from getting this number 2.4. I knew the absolute abundance of 36 elements, which is a lot of elements to know. But they're all trace elements except for calcium and aluminum. Calcium and aluminum are in weight percents. I went from there to really an array of decision making. Here you have the calcium array. And what you can see is you're going from 10% calcium to 2% calcium. And the intercept there gives us a BSM, bulk silicate Mars, of about 30. So in the end, we get 30 weight percent MgO plus or minus 2 weight percent MgO, if I remember the numbers correctly. And we do that for a number of elements. But for silicon, the arrays look terrible. And so all we did for silicon is we compared 4 data points. The blue data points are the sugar-type basalts. The orange is the sugar-type lherzolite. The pink is the sugar-type olivine. And the GRS, shown here, is the surface gamma ray survey. And so that gives us a 45.5 weight percent SiO2 with some uncertainty. And we know the lherzolites are the mantle from which the magma came out. And we see that same relationship. The Earth's mantle is about 45 weight percent silica, but the basalts at the top are about 50 weight percent silica. And you can see our estimate is between the mantle rock of the sugartites and the basaltic rock of the sugartite. Over here on the far right, we have sodium versus aluminum. We use correlations like that because sodium is a volatile element. Down here, we use the isotopes of neodymium and strontium. Neodymium and its parent, samarium, are refractory, so we know that ratio for the planet. Strontium really depends on how much rubidium is in the planet, which is a volatile element. We constrain it that way. In the center and over here on the right is the potassium-thorium ratio. Now this is fundamentally important. I'll highlight this towards the end. That tells us how much heat production is inside the Earth, inside Mars, because potassium, thorium, and uranium are the heat-producing elements, and they produce more than 99% of the heat in the Earth and also in Mars. So it's from this process, and I'll highlight that potassium-thorium ratio, that we've gone from the refractory elements that are only a couple of percent down to parts per billion, to the volatile elements such as magnesium, silicon, and iron, to, in this case, potassium thorium, which is a volatile element relative to a refractory element, thorium. Now, one of the things we found in this is volatile depletion is not related to the distance from the sun. And in fact, you look at this diagram and you'll see that Mercury and Mars has the same potassium thorium ratio measured by gamma ray spectroscopy. And Mars is backed up by measurements of meteorites from Mars. Venus and the Earth are a little bit different. They're depleted relative to Mercury and Mars, and it's well worth asking the question why. The Moon is depleted relative to the Earth by a whole lot, almost a factor of 10. Why? It tells us a lot about how the Moon formed. Vesta is a very large asteroid in the asteroid belt, and it too has had its surface measured by gamma ray spectroscopy. And satellites out in the asteroid belt have less potassium. Again, why? By the way, I don't know. Then we have complications. Here we have manganese, sodium. And forgive me, please, for changing the ratio all the time. You never know what us chemists will do. And my seismological friends laugh at me sometimes out in the audience and sometimes right when I'm having a beer with them. You're crazy with your ratios. There's a reason behind it. But here's the important point. Mars and the Earth, the bulk Earth is predicted to be the blue globe, and Mars looks like the same manganese-sodium ratio. But if you look at the bulk silicate Earth measured here, it is a lower value. And that's because we say that there's manganese in the Earth's core. And we also highlight there's no manganese in the Martian core. Why? That one I have an answer. It's because the oxidation state during core formation of the Earth is much more reduced. And in that reduced state, manganese goes into the metallic phase. Not completely, but some portion of it. But when we were doing our work on Mars, we looked at the element abundance and we can look at what might be the average oxidation state. And it's also consistent with there's more iron in the mantle of Mars than in the mantle of the Earth, which means that there's less iron in the metallic core. So here is the comparison between the two planets. And in fact, this volatility scale where it says Mars this study, you can extend it to the right to estimate how much hydrogen or water that might be in the planet. So you might say that Mars started off with more water than the Earth from this diagram. If so, isn't that a positive for habitability? Something to think about. But there's two volatility trends, one for the Earth and one for Mars. Again, we ask why. And again, I don't know, but I can say I will speculate and highlight that in the coming slides. We've put together a compositional model, and before the seismologists get a seismic signal, I have given you the proportion of the minerals. I've given you an adiabatic gradient. That's because we can actually measure the surface heat flow. We can measure Martian meteorites for what was the magma temperature. We know the ages, so therefore we can plot a curve for the rate of which it's been cooling. And then on top of that, if you allow me, I go and I will calculate what the seismologist should measure for the velocity gradient in Mars. You can see here in the aquamarine color is the velocity of the shear wave, and the purple color is the velocity of the P wave or compressional wave, and in white is the density profile for the planet. And each one of these have a little step, and they really are telling us where the different discontinuities is. So in fact, over here you can see the phase change olivine to Wadsleyite. On the Earth, that is the 410 discontinuity. On Mars, it's the 1100 kilometer deep discontinuity. And you have the Wadsleyite to Ringwoodite phase change over here. And in the Earth, that is at 520 kilometers. I can never remember nor read this, but on Mars, it's around 1,300 kilometers deep. So we are actually predicting, based upon our chemistry, what is the seismic signature of the planet. Let's go and talk about the Martian core, because that's really speculation extraordinaire. Well, the one thing I can do, and I did it for the Earth, and sometimes some of my colleagues feel challenged by me. For decades, when I was a young student, I was reading papers and they said there's 10% sulfur in the Earth's core. And I said, if you extrapolate the volatility curve for the Earth and then put the sulfur in, it'd be right there, 10%. That doesn't make any sense whatsoever. So in fact, I was scared, but I said, no, there's only about 2% sulfur in the core, only about 1% sulfur in the body planet Earth. And I've been dogmatically strong about that since about the 1990s. And I've had a lot of pushback, but a lot more people have come over to the side that the Earth's outer core does not have 10% sulfur. Now, I don't know how much oxygen, I don't know how much silicon, I don't know how much other light elements are in the Earth's core, but I'm willing to put forward a model that's competitive with some of my petrological mineral physics colleagues. I know how much sulfur is in the core, and it's not enough to make up the density deficit. And the same thing is true for the Mars. And in fact, some models for Mars have suggested 25% sulfur in the core. And I said, I'm going to be a sulfur policeman and not give you more than 7 weight percent sulfur in the Martian core. And I can be very strong about this number. Now, again, that wasn't enough sulfur to compensate for the density. And so we've put forward evidence here for oxygen and hydrogen being in the Martian core. And in fact, one of the most interesting things is this one right here, number 3. I work in Sendai, Japan, and I have lunch with Eiji Otani, he was a postdoc when I was a graduate student at the Australian National University. And he says, pay attention to ringwoodite. It carries a lot of water. And in fact, if it's in contact with metal, it will give up its hydrogen and it will give up oxygen to the metallic state. I paid attention and I adopted his idea for actually having some amount of oxygen and hydrogen in the Martian core, and then calculating the right moment of inertia in my model based upon that model. So in the end, I have these two diagrams, magnesium silica, aluminum silica, is really telling us the proportions of the big elements, magnesium and silica, relative to an aluminum element. And that's a fairly important because that's a refractory element. That would tell us how much potassium and how much thorium and uranium is in the Earth. And that produces 80% of our heat, radioactive heat. Then this diagram is from the 1950s. It's called a Urey diagram, and it looks at the y-axis, which is really the amount of iron that's locked up in metals, versus the x-axis, which is the amount of oxidized iron in a planet. And you can see down here in the bottom right, the C1 chondrites have no metallic iron. And then the top left, the enstatite chondrites have no oxidized iron. We have a core and we have a mantle, so we know we have oxidized iron and metallic iron. And so therefore we sit about there. And Mars sits below that with a little less iron in the body. And as I promised you, I would speculate. Mars, we think, has more volatiles because its formation age, and what we have here is time after T0. We know the Earth, the solar system, to be 4.567 billion years old. And 2 million years after the start of the solar system, we have what's called the tau mass age for Mars. More than 60% the mass of Mars was accreted and formed. And it was still in the presence of a protonebular disk. By 10, 20, 30 million years, when we have a tau mass age for the Earth, there is no nebula disk. And so the more volatile rich Mars may be because it grew completely in a nebula disk environment. Heat production. Heat production is very, very important. You can see here the numbers for the Earth and Mars. Mars, the total radiogenic heat by our model prediction is a little over 2 terawatts. And you can see for the Earth, it's about 20 terawatts. There's a factor of 10 in the nuclear power left inside the Earth versus Mars. The heat loss, about 3 terawatts versus 45 terawatts between the two planets. However, if you take the ratio of those numbers, and we call that the planetary Urey ratio, you can see that it's 0.8 versus 0.4. If you were driving your car home today, you'd start to worry if you only have 20% heat left in your car or 20% petrol left in your car. You know you have to stop to fill up. But if you had more than a half a tank left in your car, say 0.43, you can happily ride down the road for a while. The same is true for the Earth. So what this means really is Mars has pretty much stopped its volcanism. It's got Tharsis Mons, but it's really running out of fuel to run itself. So we can ask the question, when will the Earth stop having volcanoes? When will the Earth stop having earthquakes? We can begin to address this by actually asking how much fuel is left in the gas tank of the planet. And the analog for Mars is that we're almost out of fuel for running the planet. Now, with that thought in mind, I will finish my talk by talking about the future. On Friday, I will talk about the new field of geoneutrino studies. The decay process called beta decay is very common. The isotope systems, uranium, thorium, potassium, rhenium, lutetium, rubidium, even carbon-14, all use beta decay as part of their process. Most of the decay process in the uranium-thorium series is by alpha particle emission. What happens during beta decay? You take a down quark and transform it into an up quark. And that is actually moderated by, as you see here in a spring-like fashion, a boson called a W- particle. Photons and bosons, if you will. And the transformation from a down to an up quark is accompanied by the emission from the nucleus of an antineutrino particle, that's nu bar E, and an electron. That's a nuclear electron, not electrons that exist orbiting the body that's going to decay. We call the ones that naturally occur geoneutrinos. And in a collaboration that I've been involved in since 2005 between particle physics and geology, we're measuring the Earth's emission of antineutrinos. And in this diagram, the Camlin experiment in Japan and the Borexino experiment in Italy have more than a decade's worth of information on the emission of geoneutrinos in the Earth. Why is this important? This will tell us exactly how much thorium and uranium is in the Earth. If I know exactly how much thorium and uranium is in the Earth, I know exactly how much calcium, aluminum, titanium, scandium, and the rare earths that are in the Earth. These numbers all those 36 elements that are refractory lithophile become absolutely known with the plus minus without systematic uncertainty. And so for me, I've spent a good portion of my last 15 years doing that. In conclusion, I present to you a model for the composition of Mars, and I'm using an old true technique. I highlight that the terrestrial planets are depleted in volatiles compared to primitive meteorites. I note that the earlier accretion time for Mars, 2 million years, resulted in its volatile enrichment compared to the Earth. And that may be because of it growing in a protoplanetary disk. And then the heat-producing elements in both of these planets are important for driving their engines, but it is the dominant source of energy left for driving Mars. Thank you.
¿Alguna pregunta?
Don't believe me. Yes.
Thank you again for the discussion. Learned a lot. A question that I can't escape a little bit from what you have told us already, but I was wondering in terms of the Mars quakes, if you will, what would be the cause of the Mars quakes? And if we are to understand that there's less production of heat in Mars than the Earth, would that mean that there is also not convection, for instance?
Well, thank you for the question. I'll first give a generalization and then I'll get to specifics. So on the Earth, all day today, we've had probably several hundred magnitude 2s. We've probably had tens of magnitude 3s. We've had maybe a magnitude 4 today. It's likely that we did. It's possible we've had a magnitude 5 somewhere on the planet, and I will guarantee you it's less likely to have magnitude 6, 7, 8, 9. They actually scale relatively easily, and there's a magnitude 10 about every decade, magnitude 9 about every decade, magnitude 8 about every year, magnitude 7 about every month, something like that. I don't know the exact scale. And much of this, well, in fact, there's a wonderful site, IRIS, the International Seismological Site. I can't remember the IRIS. If you just go to iris.org, you can see the distribution of earthquakes on the planet, big and small, are along plate boundaries. And if we didn't have a theory called plate tectonics, 1 year's worth of data recorded on IRIS defines all of the plates brilliantly. So it's clear that plate tectonics plays a major role in the generation of earthquakes in the Earth today, along all three boundaries, convergent, divergent, and importantly, transform. Now on Mars, on the moon, we got an earthquake record, and there were two sources, mostly contraction, dealing with solidification, drop in temperature, and the other one was meteorite impact. And I'm not a seismologist studying Mars, but much of the quakes on Mars are associated with these kinds of processes, not plate tectonics. I think one of the most important things, and it's already starting to occur in the news, is that they think that many of these magnitude 2 and 3 earthquakes that are seen on Mars, and you'll see this in the news this week and in the future, is more than likely due to water at depth in the Mars. So as the people in this town know, there's not a lot of water immediately at the surface. There's water at depth, and sometimes you've taken the water out of the depth, and you have to get water from other areas. But what we're seeing is when we take water out, or when we push fluids in, as in the case of fracking, we will cause earthquakes. And so even without pushing water in or taking water out, you get hydrologically driven pressure differentials that will cause earthquakes. And that's the interpretation right now for the magnitudes 2 and 3. So that wouldn't be a process seen on the moon because it's a dry body. But the earthquakes that we're looking for might be deep contractional earthquakes in terms of magmatic systems, or better still, a meteorite hitting the body, and it should be big. I'll be more excited with tough questions.
Yes, I would like to ask you, you are focused on the composition of Mars and there. What do you think about Elon Musk's project to settle this planet?
Could you repeat the last part? What do I think about?
Elon Musk project. Elon Musk.
Oh, Elon Musk.
Elon Musk, yes.
Yes, yes. What do I think about?
Yeah, if it's possible that in the near future we're going to settle the Mars, like he's talking about.
Okay, okay, good question. I'll answer a couple of things. I would like to point out, as I am in Mexico, Elon Musk is an immigrant to America, and I salute that, and I'm very proud of it. I'm not so proud of my country these days. Elon Musk is just one of many entrepreneurs. I think, I don't remember his first name, Bezos, the owner of Amazon, is also excited to do that. And there's somebody else excited to do that. There is zero question about it. There's money to be made. And I think this is, it's like the question of climate change. We have perhaps gotten fed up with our governments and our politicians changing the conditions. And I think it's good and healthy that rich people are spending their money doing, let's say, exploration in science. And so I have no doubt by 2030, we will be on the moon again. And I think the role that politicians will play in government regulations will be to slow the traffic down, to make sure everybody plays fairly, and to do things as best as possible, right, in quotation marks. But I think that big industries now are going to do a lot more than what governments used to do. So you think back, the exploration of the New World, that was between rich sailors and the government at some level. I think we're in that same kind of revolution. And so we have to say, yes, do it. And we have to say, carefully. Now a question from a younger one.
I get it. Yes, I have a question. Maybe you say something and I get it, but is the Mars crust homogeneous or is it heterogeneous? Or well, there are hints to say that there is something like the oceanic crust on Earth or there is no way to know?
Okay, I like that question because you're actually exploring an area I didn't talk about much today. And the first answer is going to be straightforward. I don't know. The second answer is nobody else does either. And that's important to remember because Well, I mean, sometimes you'll hear me talking strong, like sulfur. I know. Big uncertainties. But when I was a young graduate student, Ian Campbell and Ross Taylor wrote a paper, no water, no granite, no plate tectonics or something like that. And so the focus of the paper was to show how important water was in the life cycle of a planet and in making, oh, I remember, no water, no granite, no continents is the title of a 4-page paper in the Geophysical Research Letters. Very, very wonderful paper. It's been cited many times, and it's a very simple idea. If you don't have water, you can't take a basalt, alter it, squeeze it, put it down 20 kilometers, and then melt it and make a granite. Everybody likes that model, some version of it. Maybe subduct it. It's the same process. So that's how you make granites. And you could do that on Mars because there's a lot of water and there's basalt. And so when I was still a graduate student, people didn't talk about that. They talked strictly about Mars being basaltic. And then when we went to Mars and got our first APX measurement, it's a type of instrument, we had andesite right away. And then people complained vigorously, and then they recalibrated their instrument on the Earth and recalibrated and recalibrated. And they go, okay, maybe not andesite, maybe basalt. But now we have this rover that's been up there for a year or two, and it's got lots of fancy chemical analytical tools. And we have things called basaltic andesite, and sometimes you'll see the word trachyte, which is like an andesite with a lot more alkali elements. And in fact, we know from the moon, there are felsic, and that's in the general, let's say greater than 60% silica rocks. And when we go around zapping the rocks from the rover on Mars, we come up with compositions that look like it's 65 and more % silica. And what's the debate right now is how much is what? And so when we model it, because in fact, the crust is, I think, if I remember right, 4% by mass and 7% of the moment of inertia of the planet, we treated it as a basaltic andesite with a density just about 3,000 kilograms per meter cubed. Now, if you look at knocklights, the sample people was holding and showing you, that'd be about 3,100 kilograms per meter cubed. And some people would say the average Martian basalt is around 3,200 kilograms per meter cubed. I don't know if it is, and I'm pretty happy with basaltic andesite and possibly andesitic composition. I will not be surprised if somebody tells me tomorrow we have definitely found granite on Mars. I will not be surprised. Right now, I can't fold it into my model, and definitely if somebody tells me in the news tomorrow that there's granite on Mars, the next question I'm going to have is, what is the mass fraction of granite relative to basalt? And that will be decades before we know that. So surface heterogeneity has already been mapped by the potassium, thorium, or gamma surveys. You framed it in a perspective of oceanic crust versus continental crust, maybe the primitive continental crust before it was felsic. I don't think we have evidence there is a simple dichotomy of crust on Mars. I think we have lots of basalt, and I would not be surprised if we have a patchwork of non-basalts due to perhaps the role that water could play in a planet that might never have had plate tectonics. But please pay attention to the words I used. Might never have had. That's not a strong argument, plate tectonics. But really, that will be our first set of information. In fact, let me just stand here in front of you and say, have I gotten questions about my presentation before? And one of the questions is, I think your sample is biased by sugartites and it doesn't have enough knocklights and chassignites. And I go, yep, you're right. And I would say that the knocklights and chassignites that have been found from Mars are more evolved and more complicated rocks. And that my correlation that gives me a trend in the chondritic ratios has seen through the melting relationship. And so that's why I feel strong about our methodology. So I tried to highlight for you also where my model is weak and where you can start to pick it apart. And for the younger scientists in the room, that's the benefit of being an older scientist. You don't care if you're wrong. Thank you very much. I'll be around all week if you want to have a conversation with me.